Space could be divided again and again. Time could be sliced into ever smaller moments. Reality, it seemed, was smooth all the way down. But as measurements grew sharper, something subtle began to happen. At very small scales, the rules that govern atoms and particles refused to cooperate with the geometry of spacetime itself. The tools that describe gravity stop working cleanly. Distance becomes harder to define. Time loses its steady rhythm, and the idea of a smooth, continuous universe begins to look less like a fundamental truth and more like a remarkably good approximation. Somewhere far beyond everyday experience, spacetime may no longer behave as a stage on which events unfold. It may fluctuate, it may fragment, or it may emerge only when viewed from far enough away, like the smooth surface of the ocean hiding restless motion beneath. This raises a quiet but profound question. Not where spacetime becomes strange, but when. At what point does space itself stop being classical and start behaving like a quantum object? Welcome to The Sleepy Scientist. If you enjoy calm, thoughtful science like this, please like the video and subscribe to the channel, and let me know in the comments where you're watching or listening from, whether you're grounded in one familiar place or drifting quietly through space and time somewhere else. Space and time usually present themselves as stable and continuous features of experience. A room extends smoothly from one wall to another. A path connects two places without interruption. A moment gives way to the next in an orderly sequence. There is no sense that distance comes in pieces or that time advances in steps. Everything appears divisible without limit. This impression is not subtle. It is reinforced constantly by movement, measurement, and memory. A table can be measured in meters, then centimeters, then millimeters. With better tools, the same surface can be resolved into smaller and smaller lengths. No matter how closely it is examined, a space appears to allow further subdivision. Time behaves the same way. A minute can be divided into seconds, seconds into smaller intervals, and those intervals into still finer ones. The process never seems to reach a boundary. Because this behavior aligns so closely with experience, it shaped the earliest formal descriptions of the physical world. Classical geometry treated space as continuous by definition. A line had length but no thickness. A point had position but no size. Between any 2 points, another point could always be placed. These ideas were not experimental conclusions but mathematical foundations. Geometry assumed continuity because it was consistent, powerful, and matched observation. When physics began to formalize motion and force, it adopted the same assumptions. In the late 17th century, Isaac Newton described space as absolute. Space existed independently of matter and provided a fixed arena in which objects moved. Time was also absolute, flowing uniformly and identically everywhere. Events unfolded within this framework, but did not alter it. Newton's laws of motion rely on this picture. Position, velocity, and acceleration are defined using continuous space and continuous time. A body moves along a path that can be specified precisely at every moment. Forces act continuously, producing smooth changes in motion. The mathematics presumes that positions and moments can be specified with arbitrary accuracy, at least in principle. This framework proved extraordinarily effective. At human scales, classical mechanics predicts motion with reliability that borders on routine. Bridges remain standing because stresses can be calculated accurately. Vehicles move as expected because forces and trajectories behave predictably. The assumptions of smooth space and time introduce no detectable error in these contexts. The same is true far beyond everyday experience. Planetary orbits described using Newtonian gravity can be predicted centuries into the future. The positions of planets, moons, and comets follow paths that are smooth, continuous, and stable over long periods. Even before modern instruments, astronomers could calculate eclipses and alignments with impressive precision. Distances on astronomical scales reinforce the same conclusion. The average distance between Earth and the Sun is about 150 million kilometers. The nearest star beyond the Sun is more than 4 light-years away, roughly 40 trillion kilometers. These immense separations behave exactly as a continuous spatial framework would suggest. Light travels predictable paths. Objects move along smooth trajectories. No irregular structure in space interferes with these motions. Timekeeping offers a similar picture. Modern atomic clocks measure time using the oscillations of atoms, achieving precision such that they lose less than 1 second over millions of years. These clocks rely on quantum processes within atoms, yet the time they measure behaves as a continuous quantity. There is no evidence at these scales that time itself advances in discrete jumps. Even when gravity was reconceived in the early 20th century, continuity remained intact. Albert Einstein's theory of general relativity replaced Newton's absolute space and time with spacetime, a unified structure combining 3 dimensions of space with 1 of time. In this description, gravity is not a force acting through space but a manifestation of curved spacetime produced by mass and energy. Despite this conceptual shift, spacetime in general relativity remains smooth. The theory assumes that spacetime can be described by continuous geometry at every scale. Curvature may become extreme near massive objects, but it is still defined at every point. The equations describe how spacetime bends, stretches, and evolves without requiring any smallest unit of length or time. This assumption has been tested extensively. General relativity predicts the bending of light near massive objects, the precise precession of planetary orbits, the slowing of time in gravitational fields, and the existence of gravitational waves. Observations from radio telescopes, spacecraft, and detectors such as the Laser Interferometer, Gravitational Wave Observatory, often referred to as LIGO, confirm these predictions with high accuracy. Across this vast range of scales, from laboratory experiments to cosmic distances, spacetime behaves as though it is smooth and continuous. This consistency is not accidental. It reflects the fact that the underlying assumptions align well with the dominant physical processes at these scales. One reason smoothness works so well is that most measurements involve large numbers of underlying interactions. Any microscopic irregularities are averaged out. Just as a solid table appears continuous despite being made of atoms separated by empty space, spacetime may appear smooth because its fine structure, if it exists, is far smaller than the scales being probed. This idea is common in physics. Temperature feels like a continuous quantity, rising and falling smoothly. In reality, it reflects the average kinetic energy of many particles. At the level of individual atoms, energy changes occur in discrete interactions, yet the aggregate behavior is well described by continuous variables. Fluid motion offers another example. Water flowing in a river obeys equations that treat it as a continuous medium. These equations succeed because they describe behavior at scales much larger than individual molecules. At sufficiently small scales, the description fails, but only because it is being applied outside its domain of validity. Smooth spacetime may function in the same way. It may be an effective description that captures large-scale behavior while remaining silent about finer structure. The absence of observable irregularities does not guarantee that none exist. It indicates only that they do not matter for the phenomena being described. Importantly, nothing in ordinary experience forces this question into view. There are no visible gaps in space. There are no missing moments in time. Motion proceeds continuously, and measurement refines smoothly. This is precisely why classical and relativistic descriptions have endured. They describe the world as it presents itself across an enormous range of conditions. However, physics does not stop at familiar scales. As investigations pushed towards smaller distances and higher energies, new behavior emerged. Matter no longer followed smooth trajectories. Energy appeared in discrete amounts. Measurements acquired fundamental limits. Quantum mechanics revealed that continuity, so successful at large scales, was not a universal feature of physical law. The recognition that matter behaves differently at small scales raises a natural question. If particles and fields obey quantum rules, what about the spacetime they inhabit? Does spacetime remain continuous no matter how closely it is examined, or does its apparent smoothness reflect the limits of observation? The classical picture remains essential. It captures real, measurable behavior with remarkable accuracy. Any deeper description must recover this smoothness where it applies. The goal is not to discard the familiar framework, but to understand why it works so well, and where it might stop being the whole story. The idea that space and time might be more than a passive setting marks one of the most important shifts in the history of physics. This shift is closely associated with Albert Einstein, who in the early 20th century proposed a radically different way of understanding gravity and motion. Before this change, gravity was treated as a force acting between masses across space. Objects attracted one another, and the strength of that attraction depended on their masses and separation. Space itself played no active role. It simply existed, providing distances over which forces acted and time during which motion unfolded. Einstein approached the problem from a different angle. Instead of asking how objects move through space under the influence of gravity, he asked what space and time themselves are doing in the presence of matter and energy. The result was the theory of general relativity, published in 1915. At its core is a simple but far-reaching idea. Gravity is not a force in the traditional sense, it is a geometric effect. Mass and energy change the structure of space-time, and objects move in response to that structure. In this view, space-time is not an abstract backdrop. It is a physical entity with properties that can change. To understand this, it helps to separate intuition from formal mathematics. General relativity is often associated with complex equations, but the central concept can be described without them. Space-time can curve. That curvature influences how objects move. An object that is not being pushed or pulled follows the straightest possible path through space-time. In flat space-time, that path looks like uniform motion in a straight line. In curved space-time, the same principle applies, but the path itself is bent because the geometry is bent. This is why gravity can be understood without invoking a force. A planet orbiting a star is not being tugged along a curved path by an invisible pull. Instead, it is following the natural geometry of space-time shaped by the star's mass. The orbit appears curved because space-time is curved. A common analogy involves a stretched surface with a heavy object placed at its centre. Smaller objects placed nearby roll inward, not because they are pulled sideways, but because the surface beneath them slopes. While this picture has limitations, it captures the essential idea. Geometry directs motion. In Einstein's theory, mass and energy determine how space-time curves. This relationship is precise and quantitative, even though it can be described qualitatively. Dense objects such as stars and planets create stronger curvature than less massive ones. Extremely compact objects, such as neutron stars and black holes, produce curvature so intense that it dramatically alters the behavior of space and time around them. Importantly, energy also plays a role. Pressure, momentum, and energy density all contribute to space-time curvature. Light itself, despite having no rest mass, follows curved paths in the presence of massive objects because space-time is curved, not because light experiences a force. This leads to one of the earliest and most famous confirmations of general relativity: gravitational lensing. In 1919, during a solar eclipse, astronomers observed that the apparent positions of stars near the Sun were slightly shifted. The starlight had passed close to the Sun on its way to Earth, and its path had been bent by the curvature of space-time around the Sun. This effect was small but measurable, and it matched Einstein's predictions. Gravitational lensing has since become a standard observational tool in astronomy. Massive objects such as galaxies and clusters of galaxies bend light from more distant sources, producing arcs, rings, and multiple images. These observations confirm that space-time curvature is not a mathematical abstraction. It has direct, observable consequences. Time is also affected by curvature. In general relativity, clocks run at different rates depending on their position in a gravitational field. A clock closer to a massive object ticks more slowly than one farther away. This phenomenon, known as gravitational time dilation, has been confirmed through experiments involving atomic clocks placed at different altitudes. Even systems as familiar as global positioning satellites must account for this effect. The clocks aboard these satellites experience both special relativistic time dilation due to their speed and gravitational time dilation due to their distance from Earth. Without correcting for these effects, navigation errors would accumulate rapidly. These confirmations establish space-time as an active participant in physical processes. It stretches, bends, and influences motion. It is not merely where events happen, it helps determine how events unfold. Despite this dynamic role, space-time in general relativity remains smooth and continuous. Curvature changes gradually from point to point. Distances and durations can still be subdivided without limit. There is no smallest length built into the theory. Spacetime behaves like a flexible but continuous fabric. This smoothness is essential to how general relativity works. The mathematics assumes that spacetime has well-defined properties at every location. Curvature is described locally, meaning that it can be specified in arbitrarily small regions. The theory relies on the idea that spacetime can be examined at finer and finer scales without losing meaning. At the scales where general relativity has been tested, this assumption holds extremely well. From the bending of light near stars to the dynamics of galaxies, spacetime behaves as a smooth geometric structure. Even the detection of gravitational waves, ripples in spacetime produced by accelerating masses, confirms this picture. These waves propagate smoothly across vast distances, stretching and compressing space by tiny amounts as they pass. The success of general relativity reinforces the idea introduced earlier. Smooth spacetime is not a naive guess. It is a carefully tested description that works across a remarkable range of conditions. At the same time, the theory contains hints that its domain of validity may be limited. Certain solutions to Einstein's equations involve singularities, points where curvature becomes infinite and the mathematical description breaks down. The centers of black holes are the most well-known examples. These singularities are not directly observable, but their presence suggests that general relativity is being pushed beyond where its assumptions apply. Infinite curvature is not a physical prediction so much as a signal that the theory has reached its limits. Crucially, these problematic regions arise when matter and energy are compressed into extremely small volumes. In other words, they occur at scales far removed from everyday experience. This raises the possibility that spacetime behaves differently under such extreme conditions. Still, it is important to emphasize what general relativity gets right. It provides a coherent, predictive framework in which spacetime is both smooth and dynamic. It explains gravity without invoking forces acting through empty space. It unifies space and time into a single structure that responds to matter and energy. This view deepens the idea of smooth spacetime rather than undermining it. Space and time are not just continuous, they are structured. They have geometry. They participate in the physical world. Any deeper theory of spacetime must recover this behavior where it has been tested. Smooth geometry is not an illusion to be discarded. It is an accurate description within its range of applicability. Understanding spacetime as geometry sets the stage for more challenging questions. If spacetime can bend and evolve, if it carries energy and supports waves, then it begins to resemble other physical systems that are known to have underlying microscopic structure. The question that follows is not whether spacetime is real or effective, it is whether the smooth geometric picture remains valid at all scales, or whether, under sufficient scrutiny, spacetime itself must be described using different principles. For now, what matters is this. general relativity transforms space-time from a silent backdrop into an active, measurable entity. It behaves smoothly, continuously, and predictably across the universe we observe. That success must be understood before any attempt is made to go beyond it. General relativity is one of the most successful theories ever developed in physics. Its predictions have been tested repeatedly, across many decades, and in environments ranging from laboratories on Earth to the edges of the observable universe. Wherever it has been applied within its expected range, it has performed with remarkable precision. At large scales, the theory describes gravity as the curvature of space-time produced by mass and energy. This description accounts for the motion of planets, the structure of galaxies, and the expansion of the universe itself. Observations of planetary orbits, binary star systems, and galactic dynamics all align closely with the predictions of Einstein's equations. One of the clearest demonstrations of this success comes from gravitational waves. These waves are ripples in space-time generated by accelerating masses, particularly during violent cosmic events. In recent years, detectors such as LIGO have observed gravitational waves produced by merging black holes and neutron stars. The signals detected match the waveforms predicted by general relativity with striking accuracy. The timing, amplitude, and decay of these signals provide strong evidence that space-time behaves exactly as the theory describes, even under extreme conditions. General relativity also performs exceptionally well in environments involving strong gravitational fields. Neutron stars, for example, are among the densest objects in the universe. A typical neutron star contains more mass than the Sun compressed into a sphere roughly 20 kilometers across. The gravitational field at its surface is billions of times stronger than Earth's. Despite this, general relativity successfully describes the structure, stability, and gravitational influence of these objects. Black holes provide an even more extreme test. These objects form when massive stars collapse under their own gravity, compressing matter to such a degree that not even light can escape from within a certain boundary known as the event horizon. The existence of black holes was once a theoretical possibility, but it is now supported by multiple lines of evidence, including stellar motions near galactic centers, high-energy radiation from accretion disks, and direct imaging of black hole shadows. The mathematical description of black holes within general relativity traces back to Carl Schwarzschild, who, in 1916, discovered an exact solution to Einstein's equations describing the spacetime around a spherical non-rotating mass. This solution revealed the presence of an event horizon, and deeper still, a singularity at the center. At the event horizon, space-time curvature becomes extremely strong but remains finite. An observer falling through this boundary would not experience anything locally unusual at the horizon itself. From their perspective, physics continues smoothly, at least initially. From the perspective of a distant observer, however, time appears to slow dramatically near the horizon. These effects have been confirmed indirectly, through observations of matter spiraling into black holes and through gravitational wave signals from black hole mergers. Up to this point, general relativity remains internally consistent and observationally successful. Problems arise only when attention turns to the singularity itself. A singularity is a region where quantities such as spacetime curvature become infinite. In the Schwarzschild solution, the singularity lies at the center of the black hole, where the equations predict that density and curvature diverge without bound. Similar singularities appear in models of the early universe, where extrapolating the equations backward leads to a point of infinite density, often associated with the beginning of cosmic expansion. These infinities are not merely large numbers, they indicate a breakdown of the mathematical framework. Physical quantities lose their meaning, distances shrink to zero, time ceases to behave in a well-defined way. The theory no longer provides sensible predictions. Importantly, singularities are not considered physical objects in the same way planets or stars are. They are better understood as warning signs. They indicate that the assumptions underlying the theory are being pushed beyond where they apply. In particular, they signal that treating spacetime as a smooth, continuous geometry may no longer be valid under such extreme conditions. This distinction matters. General relativity does not fail gradually as conditions become more extreme. It remains accurate up to the edge of these singular regions. Only when curvature and density reach extraordinary levels does the description collapse. This suggests that the theory is not wrong but incomplete. The incompleteness becomes clearer when quantum effects are considered. Neutron stars and black holes involve matter compressed into very small volumes. At sufficiently high densities, the quantum properties of matter cannot be ignored. Electrons, neutrons, and other particles obey quantum rules that limit how closely they can be packed. These quantum effects are essential to preventing many stars from collapsing further, as in the case of neutron degeneracy pressure. General relativity, however, treats matter in a largely classical way. It does not include the quantum behavior of particles at a fundamental level. This omission is not problematic at low densities or large scales, but it becomes critical when matter is compressed into extreme states. The same issue applies to spacetime itself. General relativity assumes that spacetime can be described as a smooth continuum down to arbitrarily small scales. Quantum mechanics, by contrast, introduces fundamental limits on measurement and precision. When energy is confined to very small regions, quantum fluctuations become significant. Attempting to probe spacetime at extremely small distances requires high energies, which in turn strongly disturb the spacetime being measured. This tension suggests that singularities arise not because spacetime truly becomes infinite or ill-defined, but because the theory describing it is being used outside its domain of validity. The smooth geometric picture works exceptionally well until it encounters regimes where quantum effects cannot be ignored. Evidence for this limitation also appears in cosmology. When the equations of general relativity are applied to the universe as a whole, they describe an expanding spacetime that was denser and hotter in the past. Extrapolating this expansion backward leads to a state of extremely high density and temperature. Eventually, the equations predict a singular beginning. Yet this extrapolation assumes that classical spacetime remains valid all the way back. At early times, when the universe was extremely small and energetic, quantum effects would have been unavoidable. The appearance of a singularity in this context again suggests a boundary beyond which the classical description breaks down. It is worth emphasizing that these issues do not undermine the successes of general relativity. The theory remains the best available description of gravity and spacetime at macroscopic scales. Its predictions continue to be confirmed with increasing precision. The problems arise only when the theory is extended into regimes it was never designed to handle. In this sense, singularities serve a constructive role. They highlight the points at which new physics is required. They indicate where a more complete framework must take over, one that incorporates both the geometric insights of general relativity and the probabilistic structure of quantum mechanics. The existence of these limits motivates the search for a deeper theory. Not because general relativity fails broadly, but because it succeeds so completely within a well-defined range. Understanding where and why it stops working provides clues about the underlying structure of spacetime itself. The picture that emerges is one of layered description. Smooth spacetime geometry governs the large-scale behavior of the universe. It explains gravity, motion, and cosmic structure with high accuracy. But at extreme densities and small scales, the assumptions that support this picture may no longer hold. Recognizing both the success and the limits of general relativity sets the stage for the next step. If smooth spacetime breaks down only under the most extreme conditions, then the question becomes precise rather than speculative. At what scale do those conditions arise, and what replaces the classical description when they do? The cracks in smooth space-time do not appear everywhere. They appear only where nature is pushed to its extremes. That fact narrows the problem and gives it direction. As the limits of classical space-time become visible under extreme conditions, a very different framework enters the picture. This framework was not developed to explain gravity or cosmic structure, but to understand how nature behaves at very small scales. It is known as quantum mechanics, and it describes a world that does not behave smoothly or continuously in the way classical physics assumes. Quantum mechanics emerged at the beginning of the 20th century, not from philosophical speculation, but from experimental failure. Classical physics could not explain how atoms emit light, how energy is exchanged, or why matter remains stable. Predictions disagreed with observations in precise and repeatable ways. Something fundamental was missing. One of the first clear signs appeared in the study of heat and radiation. When physicists examined how hot objects emit light, classical theory predicted that energy should be released continuously across all frequencies. This prediction led to results that did not match reality and, in some cases, implied infinite energy output. The problem was not subtle. The equations simply did not work. In 1900, Max Planck proposed a radical solution. He suggested that energy is not exchanged continuously, but in discrete amounts. These amounts depend on frequency and are set by a fundamental constant. Energy, according to this proposal, comes in packets rather than flowing smoothly. This idea of quantization was initially introduced as a mathematical fix. Planck himself was cautious about its implications. However, the results matched experimental data precisely. What had seemed like a technical adjustment turned out to reflect a deep feature of nature. Over the following decades, this principle appeared again and again. Albert Einstein applied it to explain the photoelectric effect, showing that light behaves as if it consists of discrete energy units. Niels Bohr used quantization to describe atomic structure, proposing that electrons occupy specific energy levels rather than moving freely. Experiments confirm that atoms absorb and emit energy only in specific amounts. These discoveries revealed a sharp contrast with classical motion. In classical physics, a particle can have any energy value and follow a smooth trajectory through space. In quantum mechanics, certain quantities are restricted. Energy levels are discrete. Transitions occur in jumps rather than gradual changes. This discreteness does not mean that everything is made of tiny blocks in a simple sense. Instead, it reflects limits on what can be measured and how systems behave. The mathematical structure of quantum mechanics describes probabilities rather than definite outcomes. It predicts the likelihood of finding a particle in a particular state, not a single, precise result. One of the most important consequences of this framework is uncertainty. Werner Heisenberg showed that certain pairs of physical quantities cannot both be known with arbitrary precision at the same time. Position and momentum are a key example. The more precisely a particle's position is specified, the less precisely its momentum can be determined, and vice versa. This uncertainty is not a flaw in measurement technique. It is a fundamental feature of nature as described by quantum mechanics. No improvement in instruments can remove it. The limitation arises from how physical quantities are defined and how quantum states behave. As a result, the idea of a particle following a well-defined path through space loses meaning at small scales. Between measurements, the particle does not occupy a single trajectory. Instead, it is described by a distribution of possible positions and momenta. Classical motion emerges only when these distributions are narrow enough to approximate a single path. Probability replaces certainty at a basic level. This does not mean that quantum mechanics is vague or imprecise. Its predictions are often extraordinarily accurate. What changes is the type of prediction being made. Instead of specifying exact outcomes, the theory specifies probabilities with well-defined mathematical rules. This shift has profound implications for how reality is described. In classical physics, systems have properties whether or not they are observed. In quantum mechanics, the act of measurement plays a central role. Observables such as position, energy, and spin acquire definite values only when measured. These ideas can seem abstract, but they have direct experimental support. Interference experiments with electrons and atoms show patterns that can only be explained by wave-like probability distributions. Precision measurements of atomic spectra confirm discrete energy levels with remarkable consistency. Technologies such as lasers, semiconductors, and atomic clocks rely on quantum principles and function exactly as the theory predicts. Despite its counterintuitive aspects, quantum mechanics is not optional. It is the correct description of nature at small scales. Any theory that ignores it fails to account for a vast range of observed phenomena. The contrast with classical physics is therefore stark. Classical theories describe smooth change, continuous motion, and precise trajectories. Quantum mechanics describes discrete outcomes, probabilistic behavior, and fundamental limits on measurement. The two frameworks are not merely different in detail. They rest on different assumptions about how physical quantities exist and how they can be known. This difference becomes especially important when scale is considered. At large scales, quantum effects average out. The probabilistic behavior of countless particles produces stable, predictable outcomes. This is why classical physics works so well for everyday objects. The underlying quantum structure does not disappear, but it becomes irrelevant to most practical questions. At small scales, however, the quantum description is unavoidable. Atoms, electrons, and photons do not behave classically. Their properties are quantized. Their behavior is governed by probability rather than certainty. Attempts to force classical concepts onto these systems lead to contradictions and failed predictions. This raises a critical issue when gravity and spacetime are considered. General relativity describes spacetime as smooth, continuous, and deterministic. Quantum mechanics describes matter and energy as discrete, probabilistic, and subject to uncertainty. Both theories are supported by extensive experimental evidence. Both work extremely well in their respective domains. The difficulty arises because the two frameworks make incompatible assumptions. Quantum mechanics assumes a fixed background of space and time in which particles and fields exist. General relativity treats spacetime itself as dynamic, shaped by energy and momentum. Quantum mechanics introduces uncertainty and quantization at small scales. General relativity assumes that spacetime can be subdivided without limit. When gravity is weak and scales are large, this tension can be ignored. Quantum effects are negligible, and spacetime behaves classically. When quantum effects dominate and gravity is weak, spacetime can be treated as a fixed background. Problems appear only when both gravity and quantum effects are strong at the same time. These conditions occur when matter and energy are confined to extremely small regions. They are relevant near singularities, at the beginning of cosmic expansion, and potentially at scales far beyond current experimental reach. In these regimes, neither classical spacetime nor standard quantum mechanics can be applied without modification. The appearance of quantum mechanics therefore marks a turning point. It introduces a fundamentally different description of physical reality, one that challenges the assumptions underlying smooth spacetime. It does not merely add new details to an existing framework, it changes the rules by which physical quantities are defined and related. Understanding this contrast is essential. The question of when spacetime becomes quantum is not about replacing one theory with another. It is about identifying where the assumptions of each theory cease to apply and how they might be reconciled. The quantum world does not deny the success of classical descriptions. It explains why they work where they do. At the same time, it sets clear boundaries. Beyond those boundaries, continuity, determinism, and smooth geometry can no longer be taken for granted. This is the tension that now comes into focus. A theory built on smooth spacetime meets a theory built on quantization and uncertainty. The point at which these two descriptions intersect is where the question of quantum spacetime becomes unavoidable. Once both general relativity and quantum mechanics are placed side by side, a deeper problem becomes impossible to ignore. Each theory is extraordinarily successful within its own domain, yet when their assumptions are combined, they resist fitting together into a single, coherent description. The disagreement is not about experimental detail. It runs through the foundations of how each theory understands reality. At the heart of the issue is how each framework treats space and time. In quantum mechanics, space and time are treated as a fixed background. Particles and fields exist within this background. Their properties change with time, their positions are measured within space, but the structure of space and time themselves is assumed to be stable and given. The background does not respond to what happens inside it. This assumption is known as background dependence. The geometry of spacetime is specified in advance and remains unaffected by the quantum processes unfolding within it. This approach works extremely well when gravity is negligible or when spacetime curvature is small. General relativity takes the opposite stance. It is fundamentally background independent. There is no fixed spacetime stage. Instead, spacetime itself is a dynamic entity whose geometry is determined by the distribution of mass and energy. Matter tells spacetime how to curve, and spacetime tells matter how to move. Geometry and dynamics are inseparable. This difference alone creates tension. Quantum mechanics requires a stable framework in which probabilities evolve. General relativity denies the existence of such a fixed framework. When spacetime itself is subject to change, the basic structure required by quantum theory becomes unstable. The conflict deepens when attempts are made to treat gravity using quantum methods. In quantum mechanics, forces are typically described by quantum fields. These fields fluctuate. They exchange energy in discrete amounts. Calculations involve summing over many possible interactions, each contributing to the final probability of an outcome. This approach has been spectacularly successful for the electromagnetic force and the nuclear forces. When the same techniques are applied to gravity, serious problems arise. Gravity is associated with spacetime curvature. Attempting to quantize gravity involves treating small fluctuations in spacetime geometry as quantum excitations. In principle, this sounds reasonable. In practice, the calculations produce infinities that cannot be removed or controlled. These infinities are not minor technical issues. They appear at almost every step of the calculation. Quantities that should correspond to measurable physical effects diverge to infinite values. The standard methods used to tame infinities in other quantum field theories fail in this context. This problem became clear in the mid-20th century, when physicists began exploring quantum gravity seriously. Richard Feynman, who played a central role in developing quantum electrodynamics, examined whether similar techniques could be applied to gravity. His conclusion was cautious. While it was possible to define a quantum version of gravity at low energies, the theory became unmanageable at higher energies. The mathematical structure broke down. The underlying reason is tied to how gravity couples to energy. In general relativity, all forms of energy contribute to spacetime curvature. This includes not only mass and motion, but also the energy of quantum fluctuations themselves. As calculations attempt to include smaller and smaller scales, the energy associated with these fluctuations grows. The gravitational response to that energy then feeds back into the calculation, producing ever larger contributions. The result is a runaway effect. Attempts to probe spacetime at extremely small distances require high energies. Those energies strongly distort spacetime. The more precisely the geometry is examined, the less well-defined it becomes. The mathematical expressions reflect this instability by diverging. This behavior is very different from what occurs in other quantum theories. In quantum electrodynamics, infinities appear, but can be systematically absorbed into a finite number of physical parameters through a process known as renormalization. The theory remains predictive because only a limited set of quantities need adjustment. Quantum gravity does not cooperate in the same way. New infinities appear at every level of approximation. There is no finite set of parameters that can absorb them. Predictive power is lost. This failure is not merely technical. It reflects a deeper conceptual mismatch. Quantum mechanics assumes that uncertainties apply to physical quantities defined within spacetime. General relativity treats spacetime itself as a physical quantity. Combining these ideas implies that space-time geometry should be subject to quantum uncertainty. Distances and durations would fluctuate. The notion of a sharply defined space-time geometry would lose meaning. Yet quantum mechanics relies on precise notions of time to describe how systems evolve. Probabilities change with time. States are compared at different moments. If time itself becomes uncertain, the standard formulation of quantum theory begins to unravel. This creates a circular dependency. Quantum mechanics needs a stable spacetime to function. General relativity predicts that spacetime responds dynamically to energy, including quantum energy. Each theory undermines the assumptions of the other when applied simultaneously. The disagreement also appears in how each theory treats locality. Quantum field theories assume that interactions occur at specific points in spacetime. General relativity allows spacetime itself to be curved in such a way that the notion of global simultaneity disappears. There is no universal time slicing the universe into moments. This complicates the definition of quantum states that evolve uniformly. Despite these issues, it is important to be clear about what is not happening. There is no experimental contradiction between quantum mechanics and general relativity in regimes where both have been tested. The problem arises only when both quantum effects and strong gravity are present at the same time. In most laboratory experiments, gravity is so weak that it can be ignored. In most astronomical contexts, quantum effects average out. This separation of scales allows both theories to coexist without conflict in practice. The difficulty appears when scale is pushed to extremes, near black hole singularities, at the earliest moments of cosmic expansion, or when attempting to describe spacetime at distances far smaller than anything currently accessible to experiment. In these regimes, neither theory can be safely applied without modification. General relativity predicts conditions where spacetime curvature becomes infinite. Quantum mechanics predicts fluctuations that cannot be ignored. Each theory signals that its assumptions are being violated. This is why the question of quantum spacetime remains unresolved. It is not due to lack of effort or imagination. It arises because the foundational principles of the two most successful theories in physics pull in different directions. One framework treats spacetime as a smooth, deterministic geometry. The other treats physical quantities as probabilistic and quantized. When spacetime itself is included among those quantities, the mathematical and conceptual structure becomes unstable. This instability points toward an important conclusion. The problem is not that one theory is correct and the other is wrong. Both are correct within their domains. The problem is that neither is complete. Resolving this disagreement likely requires a new framework that reduces to general relativity at large scales and to quantum mechanics at small scales. Such a framework would need to explain how smooth spacetime emerges from a deeper description, and why quantum effects become negligible in ordinary conditions. Until such a framework is found, the conflict remains a guide rather than a failure. It marks the boundary between what is well understood and what is not. The disagreement between quantum mechanics and gravity is therefore not a flaw in physics. It is a signal. It points to scale as the deciding factor, and suggests that the nature of spacetime depends on how closely it is examined. When disagreements appear between successful physical theories, the cause is often not location, material, or environment, but scale. The same object can behave in entirely different ways depending on how closely it is examined. Physics does not offer a single description that applies unchanged at all distances and energies. Instead, it provides layers of description. each suited to a particular range of scale. This idea is familiar even outside physics. A coastline looks smooth when seen from high altitude. From closer up, it becomes jagged. At the scale of individual rocks and grains of sand, the idea of a smooth line stops being useful altogether. The object has not changed, only the scale of observation has. Physical laws behave in much the same way. At human scales, objects obey classical mechanics. Motion appears continuous. Forces produce smooth acceleration. Space and time behave as stable backgrounds. These assumptions work because the relevant scales are large compared to the microscopic structure of matter and energy. At atomic scales, the picture changes. Electrons do not orbit nuclei like small planets. Energy levels become discrete. Probabilities replace trajectories. Quantum mechanics becomes essential, not because classical physics is wrong, but because it averages over details that now matter. At even larger scales, such as those of stars, galaxies, and the universe as a whole, gravity dominates. General relativity provides the appropriate description. Space-time curvature governs motion. Time flows at different rates depending on gravitational conditions. Quantum effects remain present, but they're usually negligible because they average out across vast numbers of particles. Each of these descriptions is accurate within its range. Problems arise only when a description is pushed beyond the scale where its assumptions hold. This perspective reframes the question of quantum spacetime. The issue is not where spacetime becomes quantum in the sense of a particular place or region. It is when, meaning at what scale, the smooth geometric description ceases to be sufficient. To make this concrete, consider the range of scales involved. An atom is roughly 1/10 billionth of a meter across. A human being spans about 1 meter. Earth's diameter is roughly 12 million meters. The observable universe stretches for tens of billions of light years, each light year being nearly 10 trillion kilometers. These scales differ by many orders of magnitude. It would be surprising if the same description applied unchanged across this entire range. Physics has long recognized this and built methods to manage it. One such method is the idea of effective theories. An effective theory describes phenomena at a particular scale without attempting to capture all underlying details. It works because those details do not significantly influence the behavior being studied. Classical mechanics is an effective theory. It ignores atomic structure and quantum uncertainty, yet accurately predicts the motion of cars, planets, and spacecraft. Fluid dynamics is another effective theory. It treats liquids as continuous substances even though they're made of discrete molecules. The theory succeeds because molecular details average out at larger scales. Smooth spacetime may be an effective description in the same sense. At scales accessible to observation and experiment, spacetime behaves as a continuous geometric structure. Curvature changes gradually. Distances and durations can be measured precisely. The mathematics of general relativity works because it captures the dominant behavior at those scales. If spacetime has a more fundamental structure at extremely small distances, that structure may be irrelevant to most physical processes, just as the graininess of matter does not affect planetary motion. The graininess of spacetime would not affect everyday experience. This idea is closely connected to renormalization, a set of techniques developed in quantum field theory to deal with how physical behavior changes with scale. Renormalization formalizes the notion that different descriptions apply at different resolutions. As one moves from small scales to large ones, certain details fade away, while others become dominant. In this framework, parameters such as mass, charge, and coupling strength depend on the scale at which they are measured. The laws themselves do not change, but their effective expression does. What matters at one scale may be negligible at another. Applied to spacetime, this suggests a possibility. The smooth geometry described by general relativity may emerge from a more complex underlying description when viewed at large scales. At smaller scales, new degrees of freedom may become relevant, altering how spacetime behaves. Emergence is not a speculative concept. It is a well-established feature of many physical systems. Temperature emerges from molecular motion. Pressure emerges from particle collisions. Elasticity emerges from atomic bonds. None of these properties exist at the level of individual particles, yet they are real and measurable at larger scales. Spacetime smoothness could be similar. It may not be fundamental. It may be a large-scale property that arises when microscopic details are averaged over. This perspective helps clarify why general relativity works so well. It is not because spacetime is fundamentally smooth at all scales, but because the smooth description captures the relevant physics where measurements are made. The theory is accurate because it is applied where it is valid. It also explains why problems appear only under extreme conditions. Singularities arise when matter and energy are compressed into very small volumes. Quantum fluctuations become significant when distances shrink. These are precisely the regimes where scale matters most, and where effective descriptions are most likely to fail. Seen this way, the disagreement between quantum mechanics and general relativity is not mysterious. Each theory is an effective description tailored to a different scale. Quantum mechanics governs small systems with strong fluctuations. General relativity governs large systems where geometry dominates. The difficulty arises in the narrow overlap where both effects are important. This overlap is small but crucial. It includes conditions near black hole singularities, the earliest moments of cosmic expansion, and any attempt to probe spacetime at extremely short distances. In these regimes, neither classical geometry nor standard quantum theory can be applied without qualification. Framing the problem in terms of scale also helps avoid a common misconception. The question is not whether spacetime is quantum here or classical there. It is not about particular locations in the universe. It is about resolution. The same region of space can appear smooth at one scale and non-smooth at another. A table looks solid from a distance. Under a microscope it reveals structure. At the level of atoms it is mostly empty space. The object has not changed. The description has. The same may be true of space-time. If space-time becomes quantum only at scales far smaller than anything currently accessible, then its quantum nature would not contradict everyday experience or astronomical observation. It would simply lie beyond the resolution of existing measurements. This does not diminish the importance of the question. It sharpens it. Instead of asking where spacetime changes, the focus shifts to how small one must look before the smooth description breaks down. Understanding scale as the key variable allows the problem to be posed precisely. It also prepares the ground for the introduction of fundamental limits. If there is a smallest meaningful length or time, that limit would define the scale at which spacetime's effective smoothness ends. The search for that scale is not about finding a hidden boundary in space. It is about identifying the point at which our current descriptions must give way to something deeper. As attention moves towards smaller and smaller scales, one particular length keeps appearing in theoretical physics. It is not derived from measurement or experiment, but from the basic constants that govern nature. This length is known as the Planck length, and it plays a central role in discussions about quantum spacetime. The Planck length is named after Max Planck, who introduced the idea of fundamental natural units at the beginning of the 20th century. Planck was interested in identifying quantities that do not depend on human conventions such as meters or seconds, but instead arise directly from the structure of physical law. To construct such units, Planck combined constants that appear in both quantum mechanics and gravity. One constant sets the scale of quantum effects, another governs the strength of gravity. A third links space and time through the speed of light. When these constants are combined in a specific way, the result is a length scale. That length is extraordinarily small. The Planck length is approximately 1.616 times 10 to the power of minus 35 meters. Compared to everyday distances, it is unimaginably tiny. For context, an atom is about 1/10 of a meter across. A proton is roughly 1,000 times smaller than an atom. The Planck length is far smaller still. There are as many Planck lengths in a proton as there are protons in the observable universe. Despite its extreme smallness, the Planck length is not arbitrary. It marks the scale at which quantum mechanics and gravity become equally important. At larger distances, gravity dominates large-scale structure, while quantum effects average out. At atomic scales, quantum mechanics governs behavior, while gravity becomes negligible. The Planck length sits at the intersection of these two regimes. It is the scale at which attempts to localize energy strongly enough to probe smaller distances would inevitably produce strong gravitational effects. This is not a matter of technological limitation. It is a consequence of physical law. To measure a very small distance, a probe with very short wavelength is required. Shorter wavelength means higher energy. As the energy of the probe increases, its gravitational influence increases as well. At sufficiently high energy, concentrating that energy into a small region would cause spacetime itself to respond strongly. Beyond a certain point, increasing energy does not improve resolution. Instead, it distorts the region being measured. If enough energy is confined within a sufficiently small volume, the result would be the formation of a black hole. At that point, information about smaller distances becomes inaccessible. The Planck length emerges as the scale where this transition occurs. Below this scale, the very act of measurement disrupts spacetime so severely that the concept of distance loses operational meaning. It is no longer clear what it would mean to say that two points are separated by a smaller length. This is why the Planck length is often described as a minimum measurable length, though that phrase requires care. It does not necessarily mean that spacetime is made of discrete chunks of that size. Rather, it indicates that the usual procedures for defining and measuring distance cease to function. Operational meaning matters in physics. A quantity is considered physically meaningful only if there is, at least in principle, a way to measure it. If no possible experiment can distinguish one value from another, then the distinction may not correspond to anything real. At distances smaller than the Planck length, no known measurement process can resolve structure without invoking energies that destroy the very notion of spacetime geometry. This suggests that talking about smaller distances may be physically meaningless, even if mathematical descriptions can still be written down. This idea represents a shift in perspective. Classical geometry assumes that distance can always be subdivided further. Quantum mechanics challenges this assumption by introducing uncertainty. Gravity reinforces the challenge by making spacetime itself dynamic and sensitive to energy. Together, these effects imply a fundamental limit. It is important to be precise about what this limit does and does not say. The Planck length is not a boundary that has been observed. No experiment has directly probed distances anywhere near this scale. It is a theoretical construct derived from combining well-established constants. Its significance lies in what it tells us about consistency. If both quantum mechanics and general relativity are correct within their domains, then there must be a scale at which neither can be applied independently. The Planck length identifies that scale. This is why it appears repeatedly in discussions of quantum gravity. It sets the point at which the smooth description of spacetime provided by general relativity is expected to fail, not gradually, but structurally. Above the Planck length, spacetime behaves in a way that can be approximated as continuous. Below it, the assumptions underlying continuity may no longer hold. The theory does not say what replaces smooth geometry. It says only that smooth geometry cannot be assumed indefinitely. Some theoretical approaches suggest that spacetime may become discrete at this scale, with areas and volumes taking on quantized values. Others suggest that spacetime may be fundamentally relational, with geometry emerging from more basic interactions. Still others propose that spacetime itself is not fundamental at all. What these approaches share is the recognition that the Planck length marks a limit to the classical notion of distance. Another way to understand this is to consider dimensional analysis. The constants used to define the Planck length are not chosen arbitrarily. One governs quantum uncertainty, one governs gravitational strength, one governs the conversion between space and time. Any attempt to describe spacetime at the smallest scales must involve all three. This makes the Planck length a natural scale rather than a human-chosen one. It is not introduced to fix a problem in a calculation. It emerges from the structure of the theories themselves. This also explains why smaller lengths do not naturally appear in established physics. There is no known mechanism that allows spacetime structures to be probed meaningfully below this scale. Any attempt to do so runs into the same fundamental obstacle: energy concentration leading to gravitational collapse. The Planck length therefore acts as a conceptual boundary. It does not tell us what spacetime is made of. It tells us where our current descriptions stop making sense. This boundary should not be confused with certainty. Physics has encountered apparent limits before that were later reinterpreted. What makes the Planck length different is that it arises from combining theories that have already been tested extensively. It is not an artifact of incomplete data, but of theoretical consistency. That said, caution is essential. The Planck length is a guide, not a measurement. It points to where new physics is required, but it does not specify what that physics must look like. Treating it as a literal smallest unit of space risks overstating what is known. What can be said with confidence is this: if spacetime becomes quantum in any meaningful sense, it is expected to occur at or near the Planck length. That is where quantum uncertainty, gravitational interaction, and spacetime structure converge. Above this scale, smooth geometry works extremely well. Below it, distance itself becomes an unstable concept. The language of points, lengths, and intervals begins to lose physical grounding. This makes the Planck length a turning point in the discussion. It provides a scale at which questions about quantum spacetime become unavoidable rather than speculative. The next step is to understand why measurement fails so completely at this scale, and what that failure implies about the nature of spacetime itself. Time is usually treated as the most reliable ingredient in physical description. Events occur, time passes, and the order of cause and effect feels fixed. Even when space is curved or distorted, time still appears to provide a steady sequence in which physics unfolds. Classical mechanics depends on this assumption, and even general relativity, for all its flexibility, preserved a continuous notion of duration. If distance can reach a limit where the idea of length loses operational meaning, it is reasonable to ask whether time faces a similar constraint. The temporal analogue of the Planck length is known as the Planck time. It is defined as the time light would take to travel one Planck length in a vacuum. Like the Planck length, it is constructed by combining the constants that govern quantum mechanics, gravity, and relativity. It does not arise from experiment, but from consistency between theories that are already well tested. Numerically, the Planck time is on the order of 10 to the minus 43 seconds. This is not merely small by human standards. It is vastly smaller than any time interval that could be measured, produced, or resolved by any known physical process. Its significance lies not in its value, but in what it represents. In everyday physics, time intervals can be made shorter by using faster clocks or more energetic processes. Atomic clocks measure time using oscillations within atoms, reaching extraordinary precision. Particle physics experiments probe interactions occurring over extremely brief intervals. In all of these cases, time behaves as a continuous parameter that can be subdivided further as technology improves. Quantum mechanics complicates this picture by linking time and energy. Processes that occur over very short durations involve large uncertainties in energy. This is not a limitation of instruments. It is a fundamental feature of how quantum systems behave. Shorter times require higher energies to resolve meaningfully. On its own, this does not imply a minimum time. Quantum mechanics allows arbitrarily short intervals in principle. The difficulty appears when gravity is included. High energy densities distort spacetime. This is not a secondary effect. It is the central insight of general relativity. Energy and momentum determine how spacetime curves. If an attempt is made to probe a time interval comparable to the Planck time, the energy required becomes so large that it strongly affects the geometry of spacetime itself. At that point, the concept of a sharply defined time interval begins to fail. Just as with distance, measurement undermines itself. The physical process used to define the interval alters the spacetime structure in which the interval is being defined. The notion of a clean separation between one moment and the next becomes unstable. This instability has consequences for causality. Causality depends on the ordering of events. One event causes another if it precedes it in time, and can influence it through physical processes. General relativity refines this idea by tying causal structure to spacetime geometry. Light cones define which events can influence which others. Even in curved spacetime, causal order remains well defined. At extremely small timescales, this structure becomes uncertain. If spacetime itself fluctuates due to quantum effects, then the light cones that define causal relationships also fluctuate. The clear distinction between before and after can blur. This does not mean that causality disappears in any everyday sense. It means that the classical notion of sharply ordered time intervals may not apply at the smallest scales. Cause and effect may still exist, but not in a form that maps cleanly onto classical time. This issue becomes especially important when considering the early universe. Cosmological models based on general relativity describe an expanding universe that was denser and hotter in the past. As this expansion is traced backward, time intervals shrink and energy densities rise. Eventually, the equations predict a state of extreme density at the beginning of expansion. Near this beginning, often associated with the earliest moments of cosmic history, the timescales involved approach the Planck time. In this regime, classical spacetime cannot be assumed to exist in its usual form. Quantum fluctuations in geometry would have been unavoidable. This does not mean that the universe began at a specific instant in the classical sense. It means that the concept of time itself may not extend meaningfully beyond a certain point. Asking what happened before that point may be like asking what lies north of the North Pole. The question assumes a structure that may no longer apply. Importantly, the Planck time should not be interpreted as the smallest tick of a universal clock. There is no evidence that time advances in discrete steps of this duration. Many theories of quantum gravity do not predict time quantization in that simple sense. Instead, the Planck time marks a boundary for classical description. It identifies the scale at which treating time as a smooth, continuous parameter ceases to be justified without modification. Above this scale, time behaves in ways that align with both experience and experiment. Clocks can be synchronized, durations can be compared, cause and effect are ordered. Below it, the assumptions underlying these concepts are no longer secure. This mirrors what was seen with distance. The Planck length does not prove that space is made of indivisible units. It indicates that the concept of distance loses operational meaning below a certain scale. The same applies to duration. Time, like space, may be emergent. It may arise from more fundamental processes that only approximate continuity when viewed at large scales. At very small scales, the language of moments and intervals may not correspond to anything physically real. This perspective helps reconcile why time works so well in classical and relativistic physics. It is not because time is fundamental in all regimes, but because it is an effective concept that applies where fluctuations are negligible and geometry is stable. Recognizing a limit to classical duration does not undermine physics. It clarifies its scope. It explains why attempts to describe the earliest universe or the interior of black holes encounter conceptual breakdowns rather than smooth extrapolations. The Planck time therefore serves as a marker. It signals where familiar notions of time reach the edge of their usefulness. Beyond that edge, new descriptions are required, not because time vanishes, but because the classical idea of duration no longer applies. Together with the Planck length, it reinforces a consistent picture. Smooth spacetime with continuous distances and durations is an excellent description at accessible scales. At sufficiently small scales, both space and time may require a different foundation. The breakdown of continuity is not an anomaly, it is a clue. It points toward a deeper structure in which space-time, as it is usually understood, emerges only when viewed from far enough away. At sufficiently small scales, the idea of an empty, featureless vacuum no longer holds. What appears as nothingness in classical physics becomes active in quantum theory. Even in the absence of particles, space is not truly empty. It is filled with fluctuations that arise from the basic structure of quantum mechanics. These are known as vacuum fluctuations. In quantum mechanics, fields exist everywhere, even where no particles are present. Each field possesses a minimum amount of energy, called zero-point energy. This energy cannot be removed. It is not associated with motion, heat, or radiation in the usual sense. It is a consequence of the uncertainty inherent in quantum systems. A useful way to understand this is to consider that quantum fields cannot be perfectly still. Just as a particle cannot have both a perfectly defined position and momentum, a field cannot have both exactly zero energy and a perfectly fixed configuration. As a result, even the lowest possible energy state involves fluctuations. These fluctuations are not merely mathematical artifacts, they have observable consequences. One example is the Casimir effect, where two uncharged metal plates placed very close together experience a measurable force due to changes in the quantum vacuum between them. Another is the spontaneous emission of light by excited atoms, which occurs because the vacuum itself is not static.